Hello everyone, myself Mahalakshmi. Today in this video we are going to see about traffic flow prediction. So what does mean by traffic flow prediction and how the prediction helps us and what are the methods to predict traffic flow and the applications. These concepts are going to see in this video. So first of all, have you ever wondered how Google Maps knows where traffic will be heavy even before you reach that road? The answer lies in an exciting AI concept called evolving graph patterns, a powerful way to predict traffic flow using the science of graphs and deep learning. Now, what is traffic flow prediction? Traffic flow prediction is one of the most important technologies used in modern smart cities. It refers to the process of forecasting how traffic will behave in the future. Traffic flow prediction is one of the most important technologies used in modern smart cities. It refers to the process of forecasting how traffic will behave in the future. For example, predicting vehicle speed, traffic density, or congestion levels on a specific road segment. Every time you open Google Maps and see a red or orange line that shows heavy traffic ahead, that is the result of traffic flow prediction. This technology helps reduce travel time, save fuel, improve road safety, and make transportation systems more efficient. So, why we need to predict traffic? As cities grow, traffic becomes more unpredictable due to office timings, school hours, accidents, weather conditions, festivals, and road work. If we can predict traffic before it happens, we can avoid it. So, prediction traffic helps us Google Maps, Waze so accurate travel time, smart traffic signals adjust in timing, emergency vehicles find fastest routes. Traffic congestion is a growing global issue. Cities lose thousands of cars and millions in fuel each year. To solve this, we need systems that can predict how traffic will behave, not just react after jams occur. Finally, traffic flow prediction uses historical and real-time data to forecast future traffic conditions. Roads are represented as a graph, and evolving patterns in this graph are learned using A1 models like GNNs. It helps avoid congestion, optimize routes, and build smart city traffic systems.
Traffic data collection for flow prediction. Core data types. Traffic volume counts tell us how many vehicles pass a point. This is the most fundamental input for flow prediction. Speed data including mean and percentiles helps identify congestion and travel time reliability. Vehicle classification supports land level or heavy vehicle modeling. Occupancy or headway indicates density and helps estimate congestion level. Incident data like accidents or road closures often causes sudden changes in flow, so it's critical for prediction. Signal and timing data influence stop and go patterns, especially in urban areas. Read geometry and map metadata help improve model accuracy. Weather conditions have major impacts on speed and volume. Special events create unusual demand spikes. OD probe data from GPS or mobile phones provides a real-time movement patterns. Where to get the data? Radar and LiDAR sensors are becoming more common due to their accuracy in detecting multiple vehicle types. CCTV cameras are combined with computer vision allows automated accounting, classification and incident detections. Smartphones, GPS and telematics provides large-scale probe and based speed travel time data. Traffic APIs like Google, Here and Intrix offer real-time data, traffic flow and incident information. Sampling rates and time windows. Consistent sampling across all sensors is crucial. Different intervals can introduce bias. Traffic conditions vary drastically between peak and off-peak hours, so models should consider separate patterns for each. Shorter interval capture dynamic behavior but require more stores to processing. Processing steps. Time alignment ensure all data sources share a common timeline. Missing data must be handled using imputation, interpolation, or filtering. Sensor calibration is required because sensors drift over time. Outlier detections removes unrealistic spikes or drops caused by sensor errors. Smoothing helps reduce noise and makes traffic patterns more stable for the model. Aggregating prompt data into useful features like average speed or travel time is critical for model readiness. Good processing dramatically improves predictions accuracy.
Okay, to talk about GNN, GNN is the Graph Neural Network, which is a deep learning model designed to work on graph structured data. We know that a graph consists of nodes, vertices, which is vertices, intersections, junctions, sensors are taken as nodes. Edges means the roads connecting node. The nodes are taken as edges. The edge features are given as speed, traffic density, travel time, road length, number of lanes. Unlike traditional neural networks that work on grids, images, or sequences like text, GNNs understand the irregular structure of real world networks, especially road networks, which are naturally graphs. How GNN works? GNN works through a process called message passing. Each node learns from its neighbors. The step 1 is to initial node features. Each node is given traffic features such as current speed, traffic flow, density, travel time, weather or event indicators. The step 2 is to message passing. Each node collects information from its neighbors. For example, if junction B is congested, it sends this information to A and C. The step 3 is to update node representation. Each node updates its internal state using the aggregated message. The step 4 is to stack multiple layers. More layers allowed a node to learn from hop neighbors, adjacent roads 2 steps away, global traffic patterns. This last step is to final prediction layer. The updated node features are used to predict future traffic speed, traffic flow, congestion probability, travel time. The message passing is the main feature used in this GNN. It aggregates messages from neighbors, update node state, and stack multiple layers for global context. Spatial dependency GNN is used here. Temporal dependency is used by RNN, GRU, and LSTM. The models contains GNN plus GRU, DCR, GAT. So the prediction pipeline will be build road graphs and with the nodes and edges. This uses historical data, speed, flow, density. The GNN learns spatial features. LSTM or GRU learns temporal patterns and predict future traffic speed or flow. For example, suppose junction B suddenly gets congested, GNN learns B sends congestion info to neighbors A and C. A and C update their traffic state. This pattern spreads across the network. After training, GNN can predict where congestion will go next, how fast it spreads, which roads will be slow. This makes it ideal for intelligent traffic management.
Hi everyone, let us talk about what is a city graph and traffic prediction. So probably you all know what the graph contains. It contains the nodes and edges. Here in this traffic prediction, the junctions and signals act as the nodes and the roads connecting them act as the edges. So it probably contains all the details like speed, density, time and car count etc. Why we are using graphs for traffic prediction? It captures propagation of traffic jams, understands inter-road influence, and predicts congestion direction and timing. So imagine a situation. So there are four junctions in a road, and what if the one junction gets jammed by the traffic, and how it influences the other junction? To overcome these all problems, we are using the city graph for traffic prediction. Evolving graph concept. Graph updates every time, which reflects peak hours, weather, accidents, and shows traffic evolution over time. So whenever you want to know the traffic prediction details, so you can open this city graph and able to know all the details like weathers, accidents, timings, percentage of the traffic congestion, etc. So here is a small example for the small diagram of the city graph. Here the J1, J2, J3, J4 and J5 are the junctions which act as the nodes, and in between lines are the roads which connect all the nodes and they act as the edges. So here is the sample prediction out to example. So here the junction 1, junction 3 and junction 5 have the congestion probability of 82 percentage, 67 and 41 percentage. So the junction which has the highest percentage will have more congestion, traffic congestion. So you can prefer the junction which have the lowest traffic congestion probability and you can use that. So here the preventive actions are signal timing changes, which alternate route suggestions, transport priority lanes, and navigation alerts. So imagine the having your red signal timing is 2 minutes, but according to the traffic that are formed in the junction, the signal timing can change and which extend to 4 minutes or 3 minutes, etc. And with the particular time change, the traffic may clear and you can travel on the road smoothly. So here we comes the conclusion. The smart city traffic brain graphs will enable you accurate dynamic predictions and smooth and congestion-free movement.
Let's see about the predictive versus reactive system. Why the predictive systems are better? Here are the reasons why the predictive system is better than reactive system. It predicts future condition instead of waiting for problems. It reduces the downtime and improves efficiency, saves cost by preventing failures, provides faster decision making, proves system reliability and performance, ensures users experience by avoiding delays or disruptions. Let's see by an example. Here, the J1, J2, J3, and J4 be the nodes that which implies main road, school zone, shopping area, and highway entrance, with where the speeds of the given cars are coming on an average speed. Here in step 2 we can see that the rising car count changing that in last 5 minutes, relations between connected roads, how congestion usually spreads across this network, impact of school zone. And here we can say that the car at J2 rising from 40 to 55, then 60 to 65 every minute. Here J4 inflows rising because people entering in the highway. J1 is observing car coming from J2 and J3. In step 3, prediction model run simulation. Here we use the historical data plus real-time data. The system predicts a jam will form at J1 at the next 12 minutes. This is because more cars are entering J1 than leaving. J2's school traffic is at peak. Highway entrance J4 is congested. A slowdown wave is moving towards J1. Then the system classifies the probability 76% chances of jam at J1 in 12 minutes, 64% chances of slowdown at J2. In this we can say that the preventive actions may be in J1 as green light exempted and J4 green time reduced, driver rerouted, emergency vehicle can be reacted. Here we can say that by using this predictive law in the having the Google Maps or any navigating app will says that the heavy traffic expected on the main road in 10 minutes suggests another alternative route via roadside road. So the result says that the reactive systems jam forms 120 car stacks clears in 25 minutes, where using the predictive systems jams are prevented and only 60 to 70 cars can be stacked and it is cleared within 5 minutes.
Predictive traffic system use AI plus real-time data. They are better because they reduce traffic jam. When the system knows traffic will increase, so it can change a single times, suggest alternative routes, reduce congestion before it becomes a jam, saving time. Drivers get yearly warnings. Road ahead will be busy in 10 minutes. Choose this after road faster. This helps people avoid delays, improve road safety. If the system predicts accident or heavy congestion, it can alert emergency teams, drivers to slow down, derived vehicles, population lower, less traffic jams equal to less fuel burning equal to reduced population, helps government planning. Prediction data helps build roads in needed areas, control city
traffic better. Why prediction is needed? Rapid urbanization, increasing vehicle population, congestion problems, demand for real-time solution. What happens when predict traffic early? Early warnings driver and system know problems before they happen. Smart traffic signal control. Signals automatically adjust to reduce waiting time, smooth travel. Vehicles get distributed across different roads, no overcrowding. After emergency response, ambulance and fire truck get quick fast route when the system predict congestion. Better decision making. People can plan best time to leave, best route choose, avoid peak hour rush. Key components of prediction: data collecting, data preparation, processing, pre processing, model training, prediction output, traffic control actions. Data collections: CCTV cameras, IoT sensors, GPS navigations, apps, traffic signals, and tool booths, weather and data. CCTV cameras, ambulance quits and fire trucks gets quickest routes when the system predicts congestion. IoT sensors. Vehicles get distributed across different nodes, no crowding. GPS navigation apps. Drivers and systems, no problem before they happen. Traffic signals are toolboards. Less traffic jams equal to less fuel burning equal to reduced population, weather and data event.
Hi everyone. I talk about traffic flow mitigation application. Traffic flow mitigation is a technique used to forecast the number of vehicle on a road at a future time using data science and machine learning and sensor. What the application does, a traffic flow mitigation system can predict future traffic volume, support traffic signal control, improve road safety, help city planning. Government use mitigation to plan new roads, public transport. And an introduction, traffic flow mitigation is a technique to forecast vehicle movement. Use medicine learning, deep cleaning and sensor data. Why traffic flow mitigation? Increasing urban traffic, need for real-time congestion management, support smart city development. Data sources: CCTV cameras, GPS-enabled vehicle, roadside sensor, historical traffic data, weather and event information. Next, system architecture, data collection, data processing, real-time prediction, output to traffic control center, and etc. Machine learning models, linear regressions, random forest, support vector regressions, and etc. Deep learning models, long short-term memory, greater recurrent UT, hybrid models, and real-time application, traffic signal control, navigation systems, accident prediction, smart parking systems, public transport scheduling. Intelligent traffic signal control. Traffic light execute their timing automatically based on predictivity, technical density, and real-time navigation. App like Google Map and Ola use traffic mitigation to avoid traffic jams. And Emergency vehicle clearness. Predicting traffic ahead of and clean path for ambulance, police vehicle. Improve response time and save life. And public transport predicted crowd place and peak hour. Additional buses, metro frequency, train timing. And smart city planning. Real-time data help government plan road explanation, traffic signal mod, and weather and event management help management traffic during heavy rain and festivals and sports event and political rains. Thank you to all.